pretty much everyone who has done something very, very important in C++ is here at least every other year or so. Directly interfacing with those people is just an incredible boon to your career, especially early in your career. Getting to pick people's brains on things, just hanging out, talking with people, you can't put a price on that. And you don't get those online.
So, thank you everyone for joining me this morning. Good start. It seems like all of us have had a long week. Today, I think as befitting myself coming here to visit the new world from the old world, I will be talking to you about a vision I have of a merging of old world elements, which would be type traits and compiler intrinsics, with the new world element of static reflection, which we're about to get in C++26. Short introduction. I've been working in multiple industries for more than 2 decades. Most of them were C++ Windows projects. I'm currently tech lead at Morphisec, which is a cybersecurity company that provides anti-ransomware tools based on automatic moving target defense technology, which both hides critical system resources as well as leaving behind decoys, which allows perpetrators to be caught in the act of unsuccessfully trying to find the hidden resources. I've been a committee member for, now it's getting close to 4 years, mainly involved in reflection and contracts. Which is how I started reading all sorts of interesting material, obviously. And this got me thinking. It got me thinking at some point about whether type traits and reflection and something that could be coupled together in interesting ways. Namely, I started wondering whether type traits, which are in a vast part, probably in a majority of cases, as you'll see, are currently implemented via compiler intrinsics, which are non-portable, could be going forward implemented in a portable manner via reflection, and thus help us cut the cord between compilers and standard library implementations, with a vision of one day having them completely cut loose from each other and being able to mix them any way you wish. And I've even done a proof of concept as early as around February this year. So, quick forward about some basic terms we were talking about. So the thing you're going to be hearing most about in this talk is intrinsics, aka built-ins, aka magic. There might be 1 or 2 other synonyms. They don't exactly have the same meaning, but they're close enough for me to afford using them interchangeably. What they are basically is a doorway between our world, the external world, and the internal world of the compiler, of the abstract syntax tree, the AST, which this direct access often gives fast access, fast build times. And many type traits today, most type traits today seemingly, are built directly in terms of those intrinsics. And many things use type traits, such as standard concepts, which I'm sure you're familiar with, especially after all the talks this week. So type traits are something very basic that it being implemented in a non-portable manner is very prohibitive if you want to have portability across compilers and libraries. And as you can see, if we look just at the big 3, they are really coupled together. You have libcx coming with Clang, libstd coming with HSC, I never remember which is which. Then you have the Microsoft STL implementation with Visual Studio. Luckily, at least all the 3 of them are nowadays open source. So let's talking about type traits. That's the short introduction. You've heard enough about them. Just the last talk here from Braden. Great talk, by the way. So I won't be getting too deep into them. Basically, you should look at type traits as kind of compile time meta function. They don't look like meta functions. Nowadays, there are many things that we're able to do with constexpr or consteval functions. Originally, this was the only way to do this kind of meta function. We will have even lesser need of them once we get reflection. But right now, we have this kind of, as Braden said, pattern matching. I also call it logical programming. They have all those elements. The modern way nowadays of using them, other than concepts, is with if constexpr. This is a simple example you can see here. If constexpr is a compile time if, so basically on any instantiation of this function template, only one of those ifs would actually compile. So this would compile in case the template parameter is a integral type. This would for floating point types. Here we get floating times, and anything else would wind up here. The old one, dating back to the 90s, would have been, it still is, enable if. Enable if works via what is known as sphene, that term that it's nice occasionally hearing Bjarne apologizing over this naming. That stands for substitution failure is not an error, which basically means that if you get an ill-formed expression, you don't get a hard compiler error if you can find another match for the same expression which is well-formed. So the point is that you need to get one match out of the candidates. And here we have two functions with such candidates. Now the way it works, we have here a type trait is integral. We have two types of type traits, we'll see later too. The first one is what I call query type traits, which conceptually return a Boolean, which is the value field, if it exists. So if we manage to compile to get a well-formed expression, we will get this value field, which is a Boolean. And then enable if t has a Boolean non-type parameter. By the way, these are going forward meaning name compile constant template parameters rather than NTTP, but I think we're more familiar with NTTP for now. So we have enable if wrapping all of this. Enable if is what I call a transformation or transformative type trait, whose conceptual return type is a type, not a Boolean. By default, it's void, but you can feed it any type. So we will get out of all of this, we will get a struct containing that type field, if and only if we manage to compile this expression. So that means if the is integral type trait comes up with a well-formed expression, which would have that value, which only happens if it matches one of the conditions, if it's one of the integral types, obviously. So here we get the same thing with is floating point. And here we can see, here's all the code, and we can see the new way. I think this came up in C++17. You can see this is the longer form, the old form. This is the newer form. This is abbreviated. We get underline T for dot type, colon type, and we get underline V for colon value. So we have a more compact way of writing this kind of things. As I mentioned before, we have two types of type traits. We have the Boolean query traits. You can see several examples here. Most of them operate on a single template parameter. So you perform a query on some type. Some of them are binary. This is the case here for the bottom two. Is same as is convertible. The first one obviously checks if two types are the same. The second one checks if one of them is convertible to the other one. And here is the second type, the type transformation. So here you input a type as template parameter, and you get a new type, which is the required transformation of the first type. So you have the first type with any const or volatile specification removed if it existed, L-value reference added, or making it signed if it wasn't already so. So now to implementation strategies. There are basically two ways to implement type traits. There are implementations via templates. There are basically what Braden showed you, and I'm about to as well. And there are type traits implemented via Intrinsics, and there is a wide amount of mixing between them. Now, when I say implemented via Intrinsics, I mean that ultimately the logic itself is made available via an intrinsic. Usually there are going to be some templates along the way even to get there, but those are not. Those are basically wrappers, not actually implementing the type trait logic. So, three basic building blocks we should learn about in this context. The first one is integral constant. Its goal is to wrap a value for compile time consumption. So it has two template parameters. The first one is a type. The second one is an NTTP of the type of the first parameter. And you get the value as a static constant per field. Pretty straightforward. There's more to it, but this is the only relevant part that we need to know. There are two type aliases for true type and false type. You may have seen them. So we get these aliases. True type is integral constant bool with a value true. False type has the value false. And we have another alias for the partial instantiation, which is integral constant bool with no value. And this is called the bool constant. So these aliases, all of them represent a struct with a field. And in our case, a Boolean field. It's going to be a flag, either true or false. And this obviously is available at compile time because it's a static const expr member. Now, enable if has quite a, it doesn't always have to be exactly this implementation, but it's likely to be quite typical. It's very simple. Much of what we see today is really quite simple. So we get the primary, we get first of all, the primary template. That's a base case. Everything will match that. So unless you've matched anything else, you're going to get an empty struct, which obviously doesn't have that type field. If you're getting in the first parameter or rather the second parameter, I think that is, no, the first parameter, the bool parameter. If it's true, it's going to match the second one, the partial specialization. And since it's a closer match, this is the match that it's going to be picked by a template, but template deduction. So we're going to get this. We're going to get the type. And we'll see, as in many cases, as I showed you before, we have the helper. For this kind of transformative type traits, the helper will usually be a type alias. You can see the implementation is quite straightforward. Of course, this also generates a template. We've already discussed this interesting name. Okay, so now to some examples. Well, this is the example I've already showed you before, so I'm not going to go deep into it, just to remember how enable if is typically being used. we've seen how helper templates, the underlying T, are implemented for transformative type traits. For query type traits, it's typically this kind of implementation via variable templates. It's also quite trivial. So now to some implementation strategies. We are still discussing type traits built via templates only at this point. And these are the simple ones. You want to match a null pointer in this case. This is a GCC implementation. We get the base case, a primary template. And if we match any of those, we are going to derive from true type rather than from false type, in which case we will have the type field. As Braden previously mentioned, in templates, you have to match exactly. There is no implicit conversion. So you have to get that exact type. So if we get one of those, we're going to get a match. Otherwise, only get the false type. Here is another example. The way GCC implements is signed. So we have the public-facing template, which delegates to a helper. In the helper, we see that there is different treatment of arithmetic and non-arithmetic types. The non-arithmetic, all of them are going to match this primary template. The non-arithmetic types are going to match it with a false, are going to derive from false type, all good. The arithmetic ones are always going to match more closely the second one, so they're always going to be resolved according to this one, which is a specialization. And they are going to derive from an internal bool constant helper, which is, for our purposes, the same as the main bool constant, which is instantiated with an arithmetic expression which performs the logic that we need in this case. So ultimately, we're going to derive from bool constant either true or false, or either true type or false type, which all of them are equivalent to true type, false type, or integral constant over bool, or a bool constant true, bool constant true or false respectively. They're all equivalent. And basically, I've already discussed this. This is one use of variable templates. We've seen them used as we've seen them before. The most common use is to have the main logic implemented in some kind of trait, and then have the helper wrapping that trait for our usability. In some cases, it's flipped around. We see the MSVC implementation of isConst. In this case, the helper variables are actually the ones implementing the logic. And we can see the main trait being implemented as a wrapper of bool constant over that helper variable, which is then obviously inherited from. Now we're getting closer to our end goal. We're going to discuss some compiler internals. Okay, so you're going to see some code, which is going to be coming from the three big ones. As it was before, this time it's going to be more specific, because internals are specific to whatever compiler you are using, which is kind of the point of this talk, because we want to detach that dependency. So, Clang implementation of isConst. We can see here on the upper part that we have an implementation which is based on a isConst intrinsic. By the way, those intrinsics, all the cases I've found, are named this way with an underline, underline. You are not allowed to name your variables this way, but implementations are. So if this implementation exists, it's going to pick it. Otherwise, it's alternating to a template-based implementation in the lower part. And going forward, we're going to see quite a bit of this kind of, I could call it cross-support. Is the internal present? Okay, let's have a straightforward implementation. Otherwise, let's do it the old way. And it, at some point, starts feeling a bit awkward. And so you start wondering, how maintainable is this? And how nice it would be to have only one way, and to have that one way also be portable, which Intrinsics currently are not. In other cases, they kind of gave up on supporting any old things, or perhaps they know that all the compiled versions they care about already have that intrinsic or whatever. In this case, both ways go to the intrinsic and go directly, not even one in terms of the other. This is several type traits implemented by GCC. Also, all of them implemented via Intrinsics. As I mentioned before, in all cases, you will get some template along the way, but that's not what really matters. Type traits will always be templates. What matters is the lower level. Here we can see another case. I think it's a little bit more interesting than the previous ones. Again, we can see that the preference is for implementing via the intrinsic if it is present. And what I find interesting is that the template-based implementation in this case is also very trivial. So the fact that they bothered with this shows me that there's great reason to actually prefer those intrinsics. Not only maintainability, which I'm not sure how much is really a consideration in this case, but build times. In the Microsoft case, we can see a bunch of intrinsics here. These are all query traits. They are implemented in two ways, either via structs or via variables. I have no idea how they decide, and it means that they are either way is viable for all cases. So it's interesting how they make these decisions. Here we can see an example of cross-support. We are still in the MSVC standard library implementation, but Microsoft does support Clang, which includes their standard library. So we can see that if Clang internal is available, we're going to implement via that internal. By the way, there is no such usage of any of Microsoft's own internals, only the Clang internal. So in all the other cases, it looks quite simple. We were just delegating something via one line. That something couldn't possibly be very complicated. And I'm going to tell you that this is one of the simpler ones, which just required me slightly minimizing the font to get it into one screen. This is actually the whole thing. That's wonderful. Okay, so the next thing I did was a little bit of graphs. I wanted to look into the proportion of how, more or less, what portion of type traits in each standard library implementation are implemented via intrinsics and what portion only via templates. So I use some graph with some dot files. So the first thing you see, you just need to look at the structure here. This is MSVC. On the left side is the part which is implemented only as templates. I've marked, for each one, I've marked a kind of lower nexus, some artificial kind of thing. The blue one is for the templates. If you get to that, it means you got to the logical implementation based on templates. The red nexus means you got to some basic intrinsic that implements a trait. And what you can see here is that about a third, by the way, this covers about half the type traits, and it's not very scientific. I'll talk about caveats later, but it's just to get a feeling of it. So the left side, so we get about a third in terms of width, which is templates, based on templates. And we can see that the templated part is also considerably higher than type trait part, which indicates some layered, deeply layered structure. And this is what that part looks at when zoomed in. You can see it's not only lots of layers, it's also quite tangled. On the lower part, you will see arrows that you don't see their end because they're still intermissing. So those are arrows going far to the right and creating dependency on type traits. So those would be, in most cases, mixed type traits, but implemented via both templates and intrinsics. This might be, for example, compound type traits, which are made up of more fundamental type traits. This is the mid area where we're finishing up with the template-based one, getting to, now we're deep into type trait area. This is, in all cases, this is going to be much clearer. All of this is straightforward. Now we're getting to Clang. This is completely opposite to what we've just seen. This is the left part is much, much smaller and also much shallower. Actually, it's almost as shallow as all the rest of them, the type trace, the intrinsic-based ones. And if we zoom in, it's indeed much cleaner. So even the minor part in Clang, which is implemented only based on templates, is much cleaner than the tangled web we've seen with the Microsoft libraries. And part of this is also actually internal, so you got even less templated type traits. So obviously everything else is also clean here. And finally we have GCC. GCC is somewhere in the middle. It's both in terms of depth as well as width, is less than Microsoft, more than Clang. As I understand GCC's history, they seemingly started off somewhere similar to Microsoft and then started drifting more and more towards the Clang way of doing things, based more and more on intrinsics. And the entanglement here is also somewhere in between. It's less than Microsoft, more than Clang. Type traits, all of them are okay. So some analysis of what we've just seen. As I said, we have MSVC. We have a convoluted set of template-based type traits, quite a few of them. They came quite late into the intrinsics world. Pay attention to the differences in width. Now we go to Clang. You see how it's about a quarter, I think, of what Microsoft has. And we have GCC, the sweet spot in the middle. Some assumptions and caveats that went into those graphs. There are cases where both intrinsics and intrinsic-based and alternative-based implementations are available, as I've shown you in the code example. In those cases, to simplify the graph, I prefer to show only the intrinsic-based ones because I'm interested in portability going forward into the future. I'm only depicting standard type traits. In cases of intervening layers with templates, which is basically, well, some of them I've shown them on the graph, but there are all sorts of helper templates and so on. I didn't want to overcomplicate those graphs, so I stripped them off it. And as I said, this covers about half the standard type traits. And yes, as you can see, all of us make errors. Who knows what might have been. As I mentioned, there is cross toolchain support. The Microsoft standard libraries are built also to compile with Clang. The Clang libraries are able to be compiled by GCC. I don't know what GCC supports. I haven't really looked into it. But again, that's one library implementation supporting one other compiler in each case. It's nowhere near close universal cross support. So a short recap. We currently have type traits which are in many cases mainly when implemented via templates. They are very complicated, hard to follow. You've seen in if you've seen Bryden's presentation how complicated templated stuff can look like also on some of my slides. I wouldn't want to have to maintain such a thing. And you know about those cryptic error messages, which were supposed to get better with concepts, which only kind of half happened. And mentioning maintainability, some of those type traits are composite type traits. So if, for example, you have an isScalar type trait, this could contain isIntegral, isEnum, isFloating point. IsIntegral itself needs to list all the integral types. You add a new type, you need to remember to add it to that list. So this requires constant maintenance. Also, obviously, with the tangled template implementation, we're going to get slower build times. And you might have heard of some type traits which are simply not implementable in any other way but via so-called magic, which is another word for intrinsics. And they're about to get another way to be implemented, which is reflection. So let's talk about reflection. First of all, we are mentioning static reflection. So what does static mean? Static, first of all, is a wonderful world in C++. We always like to dream up of more ways of using this world. We always think in the standards committee that there's just not enough meanings to this world. But for our purposes today, static means compile time, as opposed to dynamic, which is the way other languages usually do their reflection. So as to the current state, first of all, it's approved. It's in C++26 unless it gets taken out, which is increasingly unlikely at this point. It's been approved with a value-based approach, as we'll see shortly. There was also a type-based proposal. It includes introspection, meaning that the code can reflect on its own properties, not yet on expressions, unfortunately. There's some limited forms of creating code. You can't create expressions. You can't create some other entities. You can add fields to public data members to structs. You can create manipulated forms of types. You can get to a specific member in a struct, and then you reify it back, and then it's as if you had written dot member name and so on. The basic perception of reflection, at least as present, is that you have the abstract syntax tree, and that's unmutable. You can create new elements, and you can add it to the tree. Now, those reflection elements that you create are produced with into something called meta-info. We'll see it shortly. So this is basically a value semantic world, which often reminds me of the preachings of Sean Parent, only use values. What was it? Okay, and one other bonus we got as a separate paper, which is also voted into C++26. That's expansion statements, template 4. That's very nice. That looks like a loop, but it's actually a heterogeneous loop, which means you can get rid of repetitive code that nowadays needs to be repetitive because it uses different types, as in looping over tuple elements, for example. So, meta-info. Meta-info is an opaque type. We'll see its definition shortly. The reason it's an opaque type is there are several reasons. The main one was this. not hindering future changes, mainly in the type model, which might be a valid concern if you're going to have a type-based hierarchy where the types are actually modeled after the types in the language. And I do personally hope that there will be a future addition to this in the form of a library which would write this and complement the type hierarchy, but as a library, not in reflection itself. The definition of meta-info is quite reminiscent to this definition of null PTRT. If you remember, null PTRT is defined as decal type null PTR. Meta-info, I think this is not actually, the definition itself is not actually going into the standard, but this is more or less what it would look like, because any reflection would be going into a meta-info. So the way to get meta-info is to reflect on something, in this case on the global namespace. And there you have it, just decal type that, and that's your meta-info. And there's a list here of entities that can be reflected. All of them can also be spliced back. It's not what we'll ultimately be getting. It doesn't include expressions, but it's nice. It's not that minuscule. We have two basic elements we must be aware of. This is the reflection operator. It used to be comprised of a single caret. Then someone realized that it needed to be disambiguated, so the second one was added. So welcome into the C++ world, the unofficial unibrow operator. The spaceship is waiting for you right over there. Yep, we are nerds. The second one is the splicing operator. The splicer reifies, so you get, it takes a reflection, a meta info, and recreates the element that was reflected. It might have been manipulated, now you can recreate it. When you reify it, you basically introduce it into the AST. And this is not really what it looks like. I had a too late detective omission. This is what it looks like. It's actually symmetric. So you get the opening bracket, the colon, expression, colon, closing bracket. So imagine you are seeing this in the next slides. All this type name stuff, more or less the same as in templates. It's you can put it wherever there's an actual type. In most cases, you probably don't have to, but it is required in some cases for disambiguation. So some quick examples from the reflection article itself. This is first of all, typically you will see constable functions doing this. If it's a function that creates a reflection, it will never run at runtime. So it's going to be a constable function. And we can see here it expects an index, and then it will return a reflection of the member in the struct at that index if the index is legal. And we can see here the first invocation, a legal index is used. So it's as if we had written s.j equals 42. The second one is ill-formed, and in such cases, you are likely to get an error saying the expression is not constant. Another example, we see here a transformation. We have, it's worth mentioning, first of all, that we have lots of stuff that's nowadays available in constexpr code, and we get more and more with time. And those things are also available here. This is basically constexpr or constable code. And we have here std_array, which is a constexpr compatible container. And we are preparing a list of reflections of types and getting out of this function, well, this is not a function really, but we're transforming it via a range transform algorithm with a stud meta function, size of, we are transforming it into a list of sizes of those types. And this is This is a function, but that's not the constable function I previously mentioned. We are here actually creating a const expr function, which may run at either compile time or runtime, but we are creating it via an expansion statement so that it would translate an enum value to the corresponding string. So we can see if we were doing it nowadays, we would have to do a if-else if or best case some switch case. But here we just go over the possible values, the enumerators of that enum, and we are spewing out the proper string identifier in something that looks like a loop, which at runtime won't really be a loop. And just a short word about the discarded candidate. Like I said, it was supposed to be a hierarchy of types instead of one opaque meta-info type. Types instead of values. It would have offered a complex object-oriented API. And one of the concerns, there was a concern about future language changes not being future compatible, but also the concern of being hard on build times. There was a paper which tried to dispute the first concern. It claimed that build times this can be worked out so that build times will not be meaningfully impacted, but there is still a second concern. And that's all I'm going to say about that. So now we get to our main topic, what we can do with reflection and type traits taken together. So this is our question for today. Can we really take those intrinsics entirely out of type trait implementations? This is where I give you a few seconds if you want to shoot this barcode. So I did this obviously on Godbolt, on Bloomberg's fork of GCC for reflection. I did this when I previously did this presentation at CPP Online I think it was in February. Microsoft Copilot had just introduced its Think Deeper mode, so it was very helpful because reflection has lots of APIs. It's hard to manually come up with this code. It would probably do a much better job nowadays. Basically, I made up a list out of CPP reference of about half the type traits. I asked it to generate the code. And of course, it gave me ill-formed code, which I then needed to work on a few more hours, which was then incomplete. It lacked, it had some obvious mistakes, even after compiling. I needed to add more tests. And there were cases where Copilot decided that that specific trait simply cannot be implemented without, the goal was not to have any standard library dependencies other than obviously reflection. And of course, in all those cases, I did manage to implement it via reflection. And in some cases, it chose to implement it via templates, and I simplified it with reflection. And the nicest part was that once I had the full proof of concept, I said, okay, let's educate Copilot. I said, just for your knowledge, here's the correct code. I didn't ask it for anything. And it gave me right back some version of ill-formed code. That was very nice. So yeah, at least as of about 6 months ago, your job is indeed secure. Here I have only 2 slides because at this point there's really not much to show about this POC. Everything is straightforward. Here I have a bunch of query type traits. You see now it's no longer an intrinsic. Those are reflections to meta, wrapped in bool constant. And here we have the other kind of type traits, the type transformation, with type aliases. Basically here they're not even wrapped in anything. So, some discussion about this. First of all, assuming this is possible, should we base it? Should we really do it? What's our motivation? So, first of all, it's going to replace not only type trait-based, not only intrinsic-based implementations, but also template-based ones, which will generate faster compile times. When it replaces the intrinsic-based ones, theoretically it may be just a little bit slower because we're added that thin meta header library wrapper. This is only theoretic. I haven't done any measurements. I don't think they would be worth much as long as we, for now, only have experimental compilers. But there's lots of low-hanging fruit, which it would simply be a shame not to implement this way. In all the cases where we have a one-for-one match between a reflection, a meta function, and a type trait, then we should simply do it. And especially in those cases, there is a second concern about two sources of truth. Going forward in 26, you will have two ways of doing these things. You can, you as programmers, you can use the existing type traits, or you can go ahead and use reflection. And they are probably going to do the same thing, but are they? Most likely only the compiler vendor knows. Two of those are open source, the third one isn't. Good luck with that. And one of them might be buggy, so I hope you pick the right one. This is what we love in terms of course. And of course, there is a main motivation that we want to cut that cord. So, what we have discussed. Type traits are mostly implemented by a compiler intrinsics in varying proportions. We have value-based static reflection in C++26 with limited forms of code injection, mainly via splicing. We have many type traits which can conceivably be implemented via reflection instead of their current implementations. So this brings us to the big question. Beyond just type traits, can we have standard library implementations completely detached from toolchains? And the next point, if there are any vendors in the crowd, I will love to hear from them at the Q&A session. So, first of all, Meta itself has to have a norm-portable implementation. Its interface is standardized. Its implementation will always be non-portable. That's fine. It may use bespoke utilities. We must be careful not to have cyclical include dependencies. If there's something the meta header must include, then that something can't include either directly or indirectly the meta header. There is an example meta implementation. I think I remember it doesn't have any includes. That's the Clang fork. So, this is our key takeaway that we started with. It would be very nice to have decoupling between libraries and tool chains. This would be a great start, having the type traits being decoupled in the way I've described. Motivation other than single source of truth would be simply freedom. You know, we're here in the land of the free, and I'm sure you work in, some of you in big corporations, other in small ones, all like to have the freedom to choose between vendors. Some have multiple ISPs, so you don't depend on a single one. So all of a sudden you pick a compiler, it comes with a standard library. What if you want to have the be able to enjoy the strong points of the compiler with the strong points of some other unrelated library implementation. Perhaps even one of them is faster in implementing new standard features. And I believe we can get there gradually. If you imagine the current standard library is standardized, and the standard says nothing about its implementation. We can start by saying that the meta header is not portable. It's not really saying much, obviously. But then we can start saying that about more stuff. If there is more stuff in the standard library that works with Intrinsics or with any other, does any other stuff that only works well done in a certain way for a specific compiler, then those parts could also, their interfaces could also be standardized. And we could say, okay, this is another header that has a non-portable implementation, but its interface is standardized. And overall, we would aspire to have most of the standard library with a mandated portable implementation. And then you could take that part and mix it. A disclaimer I must make. I'm expressing my own opinions, not my employers. And this is not, I would say, unfortunately at the moment, a stated goal of the Standards Committee. And here we are done. I would love to take your questions and in particular to hear your input on how valuable you would find such a future and if you are implementers, where I've gone wrong with this. Thank you.
Hi, thank you. Is there anything in the standard now that would prevent library implementations from doing this? Is there something that the standard would have to change to allow this, or is this something that implementers could do with the current definition?
Well, I'm not aware of the standard saying you must do this in a non-portable manner. I think it's implied that reflection must be done this way because, you know, it exposes compiler internals which will be different for each compiler. The standard usually goes the other way. We tried to give as much freedom as possible to implementers. So it will be a tough battle going ahead and saying, no, you must implement this in a portable manner. This could be the trickiest part. Therefore, we need input from the community that motivates this.
Okay, thanks.
Thank you for the great talk. So I have a question about slide 90 or 91, something like that, where you mentioned that along with the value-based reflection, there was a type-based reflection proposal as well.
Right.
Do you have the paper number or something like that?
Well, I didn't put that in. I'm not sure it was a single paper. It was, I think it was some German guy, if I remember correctly. I can find that out. Look me up
Okay.
in the interval.
Thank you.
Any other questions? Sorry?
There was a TS for reflection.
Okay, how is that relevant? Now we're getting the real thing.
Well, because the TS...
The type-based?
Yes. The
Right. Thank you. Yes?
Could you quickly go over again the difference between using it, I think you said like code injection or generation versus slicing? Like we can only do the slicing now, right?
Ultimately, we will want to make current code generators, external code generators entirely redundant. We want to get rid of them, which means ultimately we want to have a reflection being able to generate and to reflect over any code, including especially expressions. You can't create expressions now, which means you can't create functions. You can't reflect over functions. The only thing you can't reflect over is a function prototype. So if you're implementing a function, you'll be able in C++26 to write a portable code, a portable log, for example, that automatically deduces your function return type and its parameters. And I think also the parameter names, there was some issues there. But that's all you can do. You can't either reflect over logic or generate new logic. You can create code. You can create basically entities, the static entities, the types of variables, things like that. Anyone else? Okay, thank you.